These are the answers to the stoichiometry practice quiz. When performing calculations, always show your work. Please include conversion factors with units clearly labeled. Include the proper units in your final answer and round off your answer to the proper number of significant figures. All right, number 1, consider the following reaction. Part A, balance the equation using the lowest possible whole numbers. So I see 3 atoms of calcium on the right, so we'll go ahead and put a 3 in front of the calcium nitrate on the left. I see the PO4, which is called phosphate, is surrounded by parentheses and multiplied by 2 on the right. Let's go ahead and balance the PO4 by putting a 2 in front of the potassium phosphate on the left. Now that we have 6 potassium ions on the left and we have 6 of the nitrate ions, NO3 is called nitrate, we can take care of both of those ions at the same time by putting a 6 in front of the potassium nitrate on the right. All right, this equation is now balanced, and this chemical reaction is classified as a double replacement. Part C of this question says, when this reaction was performed in a laboratory, 52.8 grams of calcium nitrate were consumed. Again, the calcium nitrate is the first chemical listed in this equation. Calculate the mass in grams of potassium nitrate, that would be KNO3, that was produced in this experiment. So we're going to set up a 3-step conversion from grams of calcium nitrate into grams of potassium nitrate. So our first step involves the periodic table. We're going to go from grams of calcium nitrate into moles of calcium nitrate. And for every 1 mole of calcium nitrate, according to the information on the periodic table, 164.10 is the molar mass of calcium nitrate. That's how many grams there are in 1 mole. Now in our second step, this involves the coefficients in the balanced chemical equation. We're going to convert from moles of calcium nitrate into moles of the other chemical, which in this case happens to be potassium nitrate. And the coefficients for those chemicals are 6 and 3. Finally, we go back to the periodic table. We're going to convert from moles of potassium nitrate into grams. And again, we use the periodic table. So for every 1 mole of potassium nitrate, there are 101.11 grams. All right, this is all set up. Now we take our calculator and do 52.8 divided by 164.10 times 6 divided by 3 times 101.11. And we get this answer, 65.0653. Let's go ahead and round that off to the proper number of significant figures. Since our measurement, 52.8 grams, has 3 significant figures, let's round off our final answer to 3 significant figures, 65.1 grams of potassium nitrate. Okay, this is number 2. Consider the following reaction and balance the equation using lowest possible whole numbers. So we have 8 carbons on the left. Let's go ahead and put an 8 in front of the carbon dioxide. We have 18 hydrogens on the left, so we'll balance that by putting 9 in front of the water. And if we do 8 times 2, we get 16 oxygens, plus another 9 oxygens from the water. That's a total of 25 oxygens on the right. We could put 12.5 or 25 halves on the left to balance the oxygen, and then go back and multiply each coefficient by 2. So our final coefficients are 2, 25, 16, and 18. And this chemical reaction is classified as a combustion. Okay, when this reaction was performed in a laboratory, 125 grams of liquid octane were mixed with 375 grams of oxygen gas. The reaction was allowed to proceed to completion until one of the reactants was completely consumed. So number 2 is going to be a limiting reactant problem. In part C, calculate the mass in grams of carbon dioxide gas that could be produced from 125 grams of liquid octane. So we'll start with 125 grams of octane. We'll do our periodic table step first, which involves converting from grams of octane into moles. And for every 1 mole of octane, we get information from the periodic table that tells us there are 114.224 grams of octane in 1 mole. Now we'll do our mole to mole conversion using the coefficients in the balanced chemical equation. We're converting from moles of octane into moles of carbon dioxide gas. And those coefficients happen to be 16 and 2. Finally, we go to grams of carbon dioxide. So for every 1 mole of carbon dioxide, there are 44.01 grams of CO2. Now we take our calculator and do 125 divided by 114.224 times 8, essentially, that's 16 over 2, and then finally times 44.01. Let's go ahead and round off this answer, 385.296. That becomes, according to the measurement, which has 3 significant figures, 125 grams has 3 sig figs, so we'll call this 385 grams of CO2. Now we don't know if the octane or the oxygen is the limiting reactant. So we're going to have to take our answer to part D and compare it to our answer to part C. So for now, all we know is that there are 385 grams of carbon dioxide from part C. Let's move on to part D. Calculate the mass in grams of carbon dioxide gas that could be produced from 375 grams of oxygen gas. So we'll start with 375 grams of O2. First, we're going to go from grams of O2 into moles. And we know from the periodic table that for every 1 mole of O2, that would be 32 grams. Now we use our coefficients. We're going from moles of O2 to moles of carbon dioxide, CO2. And those coefficients happen to be 16 and 25. Finally, we go to grams, and we know from part C that there are 44.01 grams of CO2 for every 1 mole. Now we pick up our calculator, 375 divided by 32 times 16 divided by 25 times 44.01. And we get 330.075 grams of CO2. Again, 3 sig figs in the measurement. So 375 grams has 3 sig figs. Let's round off our answer to 330, and I'll keep that dot, the decimal, at the end to show that I have exactly 3 significant figures. All right, let's compare our answers to part C and part D to figure out the limiting reactant and the theoretical yield. Okay, so we are looking at our answers to parts C and D. When we started with 125 grams of octane, we could produce 385 grams of CO2 based on our stoichiometry calculations. If we start with 375 grams of O2, our stoichiometry calculations give us 330 grams of CO2. You should know that the limiting reactant is the reactant that is used up completely. This is the reactant that leads to a smaller amount of product in the stoichiometry calculations. The theoretical yield is the maximum amount of product that can be produced, and this is based on the stoichiometry calculations that come from the limiting reactant. So we know that the limiting reactant in this particular question is oxygen, because it produces a smaller amount of product, and we know that our theoretical yield of carbon dioxide is 330 grams. So now we can easily answer parts E, F, and G to this question. The limiting reactant is the oxygen gas. Explain why you chose your answer. Because oxygen gas leads to a smaller amount of carbon dioxide in our stoichiometry calculations. That's why oxygen gas is the limiting reactant, and based on the calculations, 330 grams of carbon dioxide is our theoretical yield. All right, let's move on to part H in this question. Calculate the theoretical yield in grams of water that should be produced in this experiment. So we're going to use our limiting reactant to do this. That means we don't care about the octane at this point, we care about the oxygen. So 375 grams of oxygen. Let's see how many grams of water we can produce from this. First, it's grams to moles. Again, there are 32 grams of oxygen for every 1 mole of O2. Then we go from moles of oxygen to moles of water, and the coefficients from the balanced chemical equation are 18 and 25. And then when we go to grams, the periodic table tells us that for every 1 mole of water, there are 18.016 grams of water in 1 mole. So picking up our calculator, 375 divided by 32 times 18 divided by 25 times 18.016, we get 152.01 grams of water. When we round that off to 3 significant figures, 152 grams of water is the theoretical yield. Now we've got theoretical yield values for both CO2 and H2O. Let's take a look at part I in this question. Calculate the mass in grams of the excess reactant, again that should be the octane, that should remain left over or unreacted at the end of the experiment. We can assume for the calculations in part I that the reaction proceeds to 100% yield. Okay, so we already know that we have 125 grams of octane and 375 grams of oxygen. We've determined that the oxygen is the limiting reactant. That means that the octane is the excess reactant. And what we're trying to find is the following. How many grams of octane, C8H18, remain left over or unreacted at the end of the experiment? So there really are 2 different ways to do this calculation. I'm going to show you both methods, and you get the same answer either way. So let's assume that we started with 125 plus 375, that's 500 grams of reactants. We should end up with 500 grams of material at the end. Now we're not going to have 500 grams of products. There's going to be some octane left over. So how many grams of product do we have if we assume that this reaction proceeds to 100% yield? If we add the 2 products, again this is based on our stoichiometry calculations from the limiting reactant, 330 grams of CO2 plus 152 grams of water, the total mass of the products is not 500 grams, it's 482 grams. So 330 plus 152 is 482. Well, if there are 482 grams of product, but we started with 500 grams of reactants, that difference is the mass of octane that is left over or unreacted at the end of the experiment. So there are 18 grams of octane left over. There's another way to calculate the amount of octane left over, and again, you're going to get the same answer either way, so I will show you that method next. Okay, for this calculation, how many grams of octane were actually consumed in this experiment? And the answer we're going to get is going to be less than 125 grams, since octane was the excess reactant. So we based this calculation on the limiting reactant. Starting with 375 grams of O2, let's convert this quantity into grams of octane to figure out how much octane was consumed. Again, grams to moles. 1 mole of O2 is 32 grams. Moles of O2 on the bottom, moles of octane on the top, and the coefficients from the balanced chemical equation are 2 and 25. And then to go to grams, you will recall that for every 1 mole of octane, it's 114.224 grams. Again, this number we're going to get is going to be less than 125 since not all of the octane was consumed. So this math, 375 divided by 32 times 2 divided by 25 times 114.224 is 107.085. Let's round this off to 3 sig figs. 107 grams of octane was consumed in this experiment. But since we started with 125 grams of octane and only 107 grams reacted, that leaves 18 grams of octane left over or unreacted at the end of the experiment. So as I said, we get the same answer either way. It's your choice as far as how you'd like to calculate the amount of the excess reactant that is left over. Okay, this is question 3. In a certain experiment, a sample of potassium carbonate, that's K2CO3, reacted with a solution of hydrobromic acid, HBr, and the products were aqueous potassium bromide, carbon dioxide gas, and water. This equation is not balanced. Let's go ahead and put a 2 in front of the KBr, the potassium bromide. So now we have 2 potassium atoms on both sides. And to balance the bromine atoms, let's put a 2 in front of the HBr, the hydrobromic acid. Everything else is balanced. And let's move on to part B of this question. We have some data from an experiment. How many grams of potassium carbonate were used in this experiment? We're going to subtract the mass of the beaker plus potassium carbonate. We subtract the mass of the empty beaker, and we get 2.86 grams of potassium carbonate. Part C, calculate the moles of potassium carbonate used in this experiment. If we look on the periodic table, we can figure out how many grams there are in 1 mole of K2CO3, potassium carbonate. We'll start with 2.86 grams, put grams of potassium carbonate on the bottom, and then 1 mole of potassium carbonate on top. And according to the information from the periodic table, there are 138.21 grams of potassium carbonate in 1 mole. Since our answer will come out in terms of moles, 0.020693 moles, let's round that off to the proper number of significant figures. 2.86 has 3 sig figs. The first 2 zeros don't count, so we get 0.0207 for our answer to part C. All right, let's move on to part D. In part D, it says, based on the balanced chemical equation and your answer to 3C, calculate the moles of hydrobromic acid that would be required to react completely with the sample of potassium carbonate that was used in this experiment. So if we take 0.0207 moles of potassium carbonate and we convert this into moles of HBr, hydrobromic acid, that will be a simple 2:1 mole ratio based on the coefficients in the balanced chemical equation. So 0.0207 times 2 is 0.0414 moles of HBr. Now let's be clear, this is the amount of hydrobromic acid that is needed. That's how much is required to react. In our next part, part E of this question, we're going to figure out how much hydrobromic acid is available based on the information from the data in this experiment. So on to part E. In this experiment, 10.0 milliliters of a hydrobromic acid solution was added to the beaker, and this hydrobromic acid solution has a concentration of 6.00 moles per liter. Calculate the moles of hydrobromic acid that were added to the beaker in this experiment. So if we take 10.0 milliliters, because the concentration is in moles per liter, let's convert milliliters into liters. And we know that there are 1,000 milliliters in 1 liter. The concentration of this HBr, hydrobromic acid, is 6 moles per liter. So there are 6 moles of HBr for every 1 liter. If we do this math, 10 divided by 1,000 times 6, we get 0.600, again that's 3 significant figures, moles of HBr. Now this is the amount that was available. This is how much was poured into the beaker. Look at the two numbers. 0.0600 is greater than the amount 0.0414. So notice that the amount of HBr that is available in this experiment is greater than the amount of HBr that is needed to react with all of the potassium carbonate. So this information shows us that the HBr, the hydrobromic acid, was added in excess. They added more than was needed. So the HBr is the excess reactant. So in part F, Based on your answer to 3D and 3E, circle the substance that represents the limiting reactant. Again, hydrobromic acid, HBr, is the excess reactant because the amount of HBr available, what was used in the experiment, is greater than the amount of HBr that was needed. So that makes potassium carbonate the limiting reactant because it would be used up completely, whereas the HBr, hydrobromic acid, was in excess. All right, in part G, calculate the theoretical yield in grams of potassium bromide that should have been produced in this experiment. Again, this is based on the limiting reactant. Since our limiting reactant is the potassium carbonate, let's start with our potassium carbonate and let's go to grams of potassium bromide, which is KBr. Our first step will be from moles to moles. So moles of potassium carbonate on the bottom, moles of potassium bromide, KBr, on the top, and the coefficients are 2 and 1. In the periodic table, we discovered that the molar mass of KBr, based on the atomic masses of potassium and bromide, there are 119 grams of KBr for every 1 mole. Let's do the math. This will give us our theoretical yield. This is how much should be produced in this experiment. So 0.0207 times 2 times 119 gives us 4.93 when we round this off to 3 significant figures. So 4.93 grams of potassium bromide. That's our theoretical yield. To figure out the actual yield, we have to go back to the data table. Looking at the data table, the mass of the beaker plus the potassium bromide at the end of the experiment was 57.45 grams. If we subtract the mass of the empty beaker, we get 3.98 grams of potassium bromide. That is our actual yield, not the theoretical yield. So to get the percent yield, we take the actual yield, which in this case is 3.98 grams of potassium bromide. We divide by the theoretical yield, which is 4.93 grams. That's what we're supposed to get based on our stoichiometry calculations. Multiply by 100, and we get 80.7% yield for the results of this experiment. All right, well, that represents the end of the stoichiometry practice quiz. I hope those answers and explanations were helpful. Thanks for watching, and good luck studying for your quiz.